Okay, first of all, thanks for providing this good opportunity to share in my work. Today I'm going to talk about using a large array of BGC flow to quantify the Southern Ocean biological carbon compound. This work is mainly collaborated with my postdoc supervisor, Andrew Fassbender, and Sespisky from University of Hawaii. Let's start with the story regarding the continued increase in the atmospheric CO2. I checked the most recent record. As you can see, it has been reached to 422 ppm wave, which is about 30% increase compared to the earlier record back into 1960. As you know, the ocean plays an important role in sequestrating the carbon dioxide, help us mitigate the ongoing climate change. The ocean can uptake the CO2 via the multiple pathways, including the biology, chemistry, and physics. Among these, the biologically mediated carbon export, referred to the biological carbon pump, is a key mechanism responsible for the ocean carbon sequestration. There are several key metrics that we can rely on to quantify the biological pump strength. The first one is net primary production, which indicates the total amount of carbon fixed by the phytoplankton and available for the higher traffic level. It determines the upper limit of the carbon that can be absorbed by the biological carbon pump. The second key metric is export production, which indicates the NPP minus the carbon respired by the heterotrophic component. It tells us the amount of the carbon available after the food cycling and which can be exported into the deep ocean. More specifically, the export production can be further partitioned into the distinct carbon pools, including the POC, DOC, and particular inorganic carbon PIC. Each biogenic carbon pool has different export efficiency and implication in the SCO2 flux. For example, the particle can be more efficiently transferred into the deep ocean while the gravitational sinking. By contrast, the export of DOC is less efficient, relying on the downward missing. The formation of a PIC can act as a ballast material, overall increasing the particle transfer efficiency in the ocean interior. Another key metric we can rely on is the SCO2 flux, which directly tells us the amount of the carbon that can be absorbed by the ocean as a combined effect of biology and physics. Before I move into that, I encourage you to familiarize yourself with this equation, as will be mentioned many times in the following part. Our current estimate in the global SCO2 flux are in the range between 1.9 and 3.1 petagram per year. The estimate in the net primary production fall within the range between 40 to 60 petagram per year. The current estimate in the export production also carry large uncertainty, as you can see, spanning a range of over 100%. So the current scenario is larger flux, larger uncertainty. More importantly, the uncertainty in this biological production current estimate is much greater than the SCO2 flux, which makes it challenging for us to accurately quantify the role of biology in regulating the SCO2 flux. Obviously, the most straightforward way to reduce uncertainty is to increase the spatial and temporal coverage of the observational data set. So in the following part, I will show you how we can leverage the BGC flow array to constrain these several key metrics. In my study, the first step is to use the Huang toolbox to search the flow we want to. The criteria I applied in this toolbox is I search the flow operated in the south of the 30 degrees, and this flow must simultaneously carry off 6 parameters with delay mode quality control data. In total, I obtained about 63 flows for the further analysis. This is a slide of flow unit. So this flow can direct us tell us the oxygen and nitrate concentration change. We can also further derive the secondary parameters such as POC from the backscatter, chlorophyll A from the fluorescence, and carbonate parameter by combining the flow measure pH and the empirical estimate of total alkalinity. We can also try to roughly estimate PIC concentration in the seawater from the flow observation combined with the remotely sensed POC to PIC ratio. Now I will show you how I derive the first parameter in this equation, MPP. MPP in my study was estimated from the flow observation combined with the carbon-based productivity model, CBPM. The MPP in the CBP model is a product of the biomass and growth rate. The former term can be estimated from the flow measure POC as you just heard. The later term is a function of the POC to chlorophyll A ratio and light availability, which reflect the impact of the environmental stress on the phytoplankton growth. It's worth mentioning that all of variables included in the CBPM model are also available in the satellite. So the satellite estimate MPP is also commonly used in ocean carbon study. But as you can imagine, the key service for the satellite estimate, it can only see what's going on in the surface. The advent of the BGC flow has nicely addressed this challenge, providing the near year-round and best result parameter. So some recent studies have already combined the flow observation with the CBPM model to estimate MPP. This map indicates the time integrated MPP over the growing season obtained from more than 100 seasonal cycles. If I average this result into a 5-degree band, you can see a more clear pattern. For example, the MPP is a substantial reduce in the subpolar ocean. To verify this flow estimate, I compare the historical measurement of MPP by the carbon-14 uptake. You can see we get a very exciting agreement. If we integrate MPP over this entire region, we can get the first answer for MPP. So mid-South Ocean is about 10 petabar carbon per year. Now let's move to the second metric, export production. As we learned from the textbook, the biological production level can show the carbon dioxide neutral but generate the oxygen. That means we can use different biologically relevant tracer to quantify the biological production. As you just learned from the Edison talk, the time range of change of tracer from the BGC flow are affected by the multiple physics and biological process. I'm particularly interested in the biological term, which can be computed as a residual shown on the left-hand side of the flow observation, suggested by the other abiotic term. Under the assumption of the steady state, the biological term can be equal to the export potential. By leveraging the multiple sensors carried by the BGC flow, we can constrain the biological term from 3 chemical tracers, DIC, nitrate, total alkalinity, and one biological tracer, POC. Same idea, I average this result into every 5-degree band to get the mean meridional pattern. If we look closely regarding this result, we can find that either the magnitude or the meridional pattern of the biological term solved from the different tracer, they are different. This discrepancy mainly reflects the different ability of the tracer to capture the various carbon flow dynamics. For example, the nitrate-based biological term tells us the sum of the organic carbon production, whereas the DIC and the TA-based biological term encompass additional term, PIC production. The biological term solved from the backscatter, it tells us the in-situ change of the suspended particle in seawater, which reflects the imbalance between the total POM production minus the simultaneous sinking flux out of Newport zone. Based on this information, I can link this multiple biological term and member Newton ratio to do the carbon flow partitioning. This is a carbon flow partitioning result. The panel on the left and the right illustrate the export potential of the distinct carbon flow and its associated sinking flux. Here we can see that in the subpolar ocean, the export is predominated by the POC portion, shown in blue. But in the low latitude region, and high latitude seasonal axial region, there are increasing fraction of the DOC component shooting rate. Another very interesting result is in the subpolar region. We also observe that is elevated PIC production shooting ground. Here you probably will question whether this carbon partitioning result makes sense. To verify this result, I also combine the historical data of the sinking flood combined by the Sorry to 34. Very excited, we also get a good consistency. Okay, with this information, we can fill out the second term. But most exciting part, we further open the black box of the export production to figure out the different composition of the carbon export. This information is very valuable for us to understand the functionality and the biological plant efficiency. Right now, the only unknown term in this equation is the CO2 flux. We have flow, so we can do that. The CO2 flux can be estimated from the flow measure PCO2 combined with the remotely sensed wind speed and ice coverage. This panel illustrates the annual CO2 flux from the observation. We can see that in the low latitude region, the Southern Ocean generates a CO2 sink, but it gradually shifts to the CO2 salt. To further distinguish the relative contribution of the biology and physics to the acid CO2 flux, I do a simulation. The first simulation is I remove the PIC production to stimulate the ocean in the absence of the calcite group. The second simulation is I remove all of the biological production to see how the CO2 flux will change. In a practical sense, the simulation is conducted by reconstruction of the carbonate parameter from the flow observation subtracted by the integral different carbon pool I just showed you previously. Here is the simulation result. The green bar is the acid CO2 flux in the real ocean, as I showed you in the prior slide. If I remove the PIC production, okay, we can see that the PIC will, the acid CO2 flux will increase from 0.4 to 0.7. If we further remove the organic carbon, the Southern Ocean will dramatically shift from the CO2 sink to salt, leaving about 2.1 petaCarbon to the atmosphere. Then we can compare the CO2 difference between the different productive scenarios to sort out the relative contribution of each carbon flow in regulating the acid CO2 flux. With this information, we can answer the final piece of the puzzle in this equation, and can also see how the physical and the biology will interact acid CO2 flux. Finally, I would like to take 1 minute to make an advertisement for the toolbox our group are currently working on, called the Tracer Boundary Algo Toolbox. This is already in the final test phase. You probably can see it soon. The motivation for us is try to reduce the user barrier to perform the tracer boundary corrosion based on the BGC flow data. In this toolbox, you only need to provide 3 basic parameters: flow WID, the tracer you are interested in, and the depth integration. Then the toolbox will take over everything to help you download the data from the JDAT, match up with the ancillary parameter from the ADAS, parameter the physical term, and doing the SNT estimate. Just a few minutes wait, you can get the output for the different tracer boundary term. I believe this output is really have a wide range of scientific application. You can not use to address the ocean CO2 uptake and biological plant stress, as I showed in my talk. You can also use to study the nutrient supply and biophysical interaction. That's it. I just stop here. I'm happy to take any questions.
I have a question about the MCP toolbox. Could ask this later, but are you guys using the same CBPM model for estimating MPP or something else in the network?
In the tracer boundary
Yeah.
model, in current tracer boundary model, we didn't include the MPP estimate. We just perform the tracer boundary corrosions.
That was really great. I'll read the paper. I was wondering how you could trade the PIC from the Argo books. Did you use that, or what metric measurement did you use to constrain how much PIC is?
Yeah. Let's go back to this. Yeah, in our study, we calculated two PIC revenue flag. One is the export potential of PIC. The second is the PIC sinking flag. So the first step we need to do is, as you can see, the biological term so far, the nitrate term, they didn't include the PIC, but the biological term so far, the DIC, they include the PIC term. So we can link these two biological terms with end member nutrient ratio of how the PIC and organic carbon produce, and try to solve out how many percent of the carbon export is attributed by organic carbon term and how many attributed by the PIC term. It's just something like we build up two equations. There are two unknown terms in this equation, so we can solve a set of the function to get this. I can show you more detail after the talk.
Following up on that, so the more you get into like the subtropics, the background nitrate approach is zero, right? And then so the nitrate, that's where the nitrate budget breaks down, because we know that NCP happens in the subtropical gyres, but there's no drawdown of nitrate. So how did your calculations deal with that? You know, because it's not a Redfield ratio at that point, right? You know, because yeah. So what do you think the uncertainties are there when you try to calculate the POC?
Yeah, so first of all, as you mentioned, the nitrate-based biological term estimate in the saturated ocean is very small, so it may carry large uncertainty. So the reason why we see that is a strong DIC production, but a minus trend in the nitrate term is that it's a DOC production, but DOC has very higher C-N ratio. So we combine a global data set of the DOC and the DON just published by Marit, so it's very useful. So we use this to get end member ratio of DOM as well as for the POM, so we can link these two biological terms to solve the different carbon flow contribution.